Okay, perfect. Okay, welcome everybody to the 10th MCRN Colloquium. Today we have Dr. Priyam Raghuraman from the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois, Urbana-Champaign. Excited to have him here. Today he's going to talk about insights into how the Earth accumulates heat, manifestations of radiative forcing, and feedback in the satellite record. So with that, Param, I'll give it to you.
Yeah, thanks, Christian, and thanks, Emmanuel, for the invite. So yeah, I'm Shiv Priyam Raghuraman. I full first name's Shiv Priyam, but I usually go by Priyam as well. So I'll give a brief bio in a minute, but yeah, I'll be talking about how Earth's accumulating heat and how these nice new satellite observations we have of Earth's radiative flows at the top of the atmosphere is giving us a lot of insight, along with climate models into how the Earth is behaving. So, brief bio, because many of you may not know me. I was an undergraduate at the University of Minnesota during about 2012 to 2016. I was a major in math and minored in physics. I worked with Professor Dick McGehee for my senior thesis on dynamical systems and glacial cycles. It kind of culminated in this senior thesis that I published in the Minnesota Journal of Undergrad Math. But Dick had a really infectious curiosity, still has, of the climate. And so it was great for him to be my advisor and kind of connect that math fundamentals back to the climate system. And so I ended up pursuing a PhD in atmospheric and oceanic sciences at Princeton, and then did postdocs at the National Center for Atmospheric Research and the University of Miami. And so now I'm an assistant professor at the University of Illinois. If you or you know of anyone interested in pursuing, grad school in math climate, please do reach out at this email. So, more precisely, kind of what I've studied is the energy balance of Earth in this very much not to scale figure. The energy in that we have is coming from the sun, and that should equal the energy out from the planet at equilibrium. And so this energy balance is what kind of sets the climate system and keeps our planet habitable. So at equilibrium, I'm basically saying S naught is this incoming solar radiation should equal the RSW, which is the reflected shortwave radiation, plus the outgoing long wave radiation, OLR. And I'll go over these terms more precisely in a bit. But it's obviously much more complicated than that, with several flows of energy through the climate system. And so there's clouds, there's gases, there's aerosols, there's land, there's ocean, there's ice. All of these interact with light, infrared and sunlight. And so changes in these constituents manifest then at the top of the atmosphere as radiative changes. And so you can see them now from space in the radiation. And so then these changes that we see in the radiative fluxes is then also a fundamental indicator of climate change. And as you can see at the top of the atmosphere, the math isn't mathing. 340 watts per meter square we're getting from the sun, but what's leaving the Earth is not 340 watts per meter square. It's 100 plus 239. And so currently there's less energy going out to space than what we get from the sun. And so this is leaving extra heat in the Earth system, what we call the Earth's energy imbalance. So that imbalance is mostly stored in the ocean at the left bottom, you can see. That number is now almost double since 10 years ago when this paper was published. So Earth's energy imbalance is just the incoming solar minus the outgoing radiation, that difference. So a pretty simple but fundamental question is, how and why does Earth accumulate heat? I mean, this is a pretty basic question we should know the answer to. And what are the mechanisms? And so climate models and now these observations can be used in conjunction with theory to kind of explain some of the changes we've seen in the past and give us some kind of counterintuitive answers to what we think is the answer. So before kind of going into the science and figuring out the causes of the changes in the Earth's energy balance, why is it even important figuring this out? And so I show a schematic of symptoms of an imbalanced Earth here, where we have extra heat in the system currently because we're not sending away enough energy. And so the big picture takeaway is that a surplus of energy in the system leads to like an increase in atmospheric temperature, atmospheric moisture, global sea level rise, global surface temperature rise, sea ice decreases, land ice decreases, and over land, these more extreme events, more flooding, more drought, less glaciers. And so it's then really fundamental to figure out how and why our energy balance is changing. What principles can we boil this down to that gives rise to these changes of the overall imbalance, not these specific terms. And so NASA has been has sent since March 2000. It's been recording a lot of our observations of Earth's radiation budget. And so I won't have as cool visuals as NASA, so I thought I would just show you NASA's own video of how does a satellite observation work.
In order to understand the Earth's climate, it's critical we understand how warm the planet is, how its temperature changes over time, and what factors can force those changes. The sun is the Earth's primary source of heat, constantly bathing us with solar radiation. The land surface, cloud cover, and our atmosphere help determine how much of that heat is reflected and how much is retained.
How that changes over time is really critical, because in a climate system that's in equilibrium, those two should really balance. And if they do, then the temperatures will remain relatively constant with time. Now, when you add greenhouse gases such as carbon dioxide, methane, you change that radiation balance at the top of the atmosphere. You reduce the amount of outgoing radiation, and so that imbalance means more energy is in the system. Part of it goes into the ocean, as it's stored in the ocean, and part of it goes into actually warming the Earth.
One of NASA's most important tools for measuring that heat is an instrument on board the Aqua, Terra, TRIM, and NPP satellites called CERES, Clouds in the Earth's Radiant Energy System.
CERES instrument has exactly 3 channels, but those 3 channels have been tuned to get really, really important information about long-wave radiation from the Earth system, the reflected short-wave radiation from the sun, and then a window channel of radiation. So it's got 3 channels that give us a huge amount of information about the radiation budget of the Earth.
CERES observations complement data from another instrument on Aqua and Terra called MODIS. MODIS has a smaller footprint, but much higher resolution to its data, illuminating how the energy budget is affected by clouds, dust particles, oceans, and land cover. That energy budget can also be influenced by natural events, such as the La Nina and El Nino weather patterns, the amount of ice and snow covering the Earth, and events that impact the Earth's atmosphere, like volcanoes. Researchers use CERES data and similar data sets from the past to establish a long-term trend that encompasses all those factors and the natural variation of the Earth's radiation budget.
If you want to look at changes in the system that are significant, that might be associated with actual global warming, you have to measure above that natural variability. So you need a long record.
The CERES instruments and their predecessors have been taking the Earth's temperature for almost 30 years, and this data can be used in conjunction with other measurements of the Earth's vital signs.
And so having the CERES measurements, the ocean heat.
Awesome. So yeah, Norman gives a great update and a lot of information on how these satellite observations work. And so what are the factors at play now that we have these observations of the radiation? How are they temporally changing, and why is that changing? So yeah, satellite observations have been kind of measuring the radiation emanating at the top of the atmosphere over the last 2 decades plus now. And so one major factor can be that we have an external perturbation. such as human-caused greenhouse gases or aerosol pollution changes in the atmosphere. Aerosols are basically, they come from combustion of fossil fuels, and it increases during much of the 20th century, kind of cool the planet. And we'll get back to this later, where in the 21st century, this pollution has come down a lot and has important impacts on the Earth's energy balance. This is what we all kind of encapsulate into what we call the effective radiative forcing term, this external perturbation. It need not also just be, human caused changes. We can also, this external change can be something like the sun sending us more energy. And so overall, we consider this the external perturbation, which is the sum of the kind of instantaneous change in the radiation budget, the IRF, instantaneous radiative forcing, plus then some adjustments that the atmosphere makes before the surface temperature response. Now this kind of perturbation causes a temperature response to try and restore the planet back to equilibrium. And now in that process, there are various feedback processes that can then amplify or diminish the temperature response. And so an example is water vapor. So say you increase CO2 in the atmosphere, you would have a warmer planet, a warmer atmosphere, and a warmer atmosphere can hold more water vapor. Water vapor is a great greenhouse gas, so then it traps more infrared radiation, which then heats the planet more, and then more water vapor is in the atmosphere, and so on and so forth. So that's what we call a positive feedback. Now the IPCC, the Intergovernmental Panel on Climate Change, it kind of assesses and synthesizes like thousands of papers of literature. And so it can kind of break down this climate feedback into different processes. And so what we call climate feedback is lambda, and it can be kind of, for a small term, it can be broken down into a small perturbation, it can be broken down linearly into what we call the Planck feedback, the water vapor feedback, the surface albedo feedback, and the cloud feedback. And so it's a negative term, this net climate feedback, lambda, mainly because of the Planck feedback. So what's the Planck feedback? It's just simply a warmer body emits more radiation to space. And so this can be kind of derived directly from Stefan Boltzmann's law, the derivative of it. And you can get that, a warmer body emits more radiation out. So it's a cooling influence, diminishing global warming. So that's why it's negative. Water vapor is a positive feedback, as you can see. And then the surface albedo feedback is also positive. This is because when you have ice, like sea ice and land ice, it reflects a lot of sunlight back to space. But when you warm, that ice kind of disappears and exposes you to more open ocean water, for example. And so then that heats up the surface more, which then melts more ice, and so on and so forth. So that's a positive feedback because it's amplifying that temperature response. Now you'll see that there's a big uncertainty in that cloud feedback, and I'll spend some time on what this exactly means, but how clouds respond to global warming is a big uncertainty in how much they'll amplify or maybe even diminish global warming. And that's where actually most of the spread in that net climate feedback, all the reds and blues and greens are basically like model estimates of what they should be, but it's all coming from the cloud feedback. Now, aside from the kind of the external aspect, there are just internal variations in the climate system, such as the El Nino Southern Oscillation, or just atmospheric noise in the system. The butterfly effect, for example, where Lorenz had kind of termed this in the mid-20th century, that a small initial condition difference can lead to a different climactic state. And so I look at then how all the energy budget is kind of being changed by each of these factors. So getting to actual data, I'm plotting here the satellite observed time series of the Earth's energy imbalance. I plotted here as anomalies, interannual anomalies. So it's the actual imbalance minus the kind of climatology, the mean of the period removed. And I do this because the observations have some hard time getting the absolute value of the energy imbalance correctly. But the delta EEI, the change, is a direct measurement that we have a lot of confidence in. And there's been a lot of other observational work from the ocean, from geodetic measurements, et cetera, that all kind of show a similar trend. And so what I want to point out is that, yes, you can see these increases and decreases. So in 2010, for example, it's the anomaly is almost -1 watt. So that's the mean over this period is about a watt. So it's almost dipped down to 0. But overall, you can see that there's a steady increase in Earth's energy imbalance. I guess watts per meter square, I just want to clarify, is our heating rate of the planet already. So then this trend that we see of about 0.38 watts per meter square per decade is an acceleration of heat content on the planet. It's a second derivative. So yeah, why is Earth's energy imbalance increasing? That's the main question. The null hypothesis would just be it's due to internal variability, or if not, is it human influence? And so I'm going to signpost at the right top where I'm talking about EEI first, and then I'll talk about the long wave component, outgoing long wave radiation, and then the reflected short wave radiation. So all results are in the global mean mostly, unless I kind of specifically refer to it. So global average radiation changes. Now, observations can tell us how the planet is changing, but not why. So it'll give us, that time series. So it'll give us the change, but it doesn't tell us why that change is happening. So we have to investigate the why using models, and specifically climate models. And I'll kind of show you this video from the UK Met Office, but essentially climate models solve the Navier-Stokes equation numerically, equations of energy, momentum, at these discretized grids, and then it's kind of moved forward into the future. So it's a short video.
Long-term climate predictions, like weather forecasting, relies on the experience and skill of scientists combined with computer models of the climate. These models start by covering the globe in an imaginary grid or net. The grid is then mirrored many times, each above the other towards the edge of the atmosphere. The result can be imagined as many thousands of cubes on and above the Earth's surface and beneath the oceans. A picture of the current climate is then represented in each of these cubes. In climate models, this picture includes land, sea, ice, and gases, as well as temperatures, pressure, and humidity included in weather forecast models. The maths and physics that determine how the atmosphere and oceans work is well known. Scientists use powerful computers to host the models, solve the mathematical and physical equations, and calculate the changes in climate in each cube in small steps many decades into the future. At any point, they can see what the future state of the climate in the cubes might be, and use their experience to interpret the computer prediction to see what the impact of the changes might be.
So yeah, these models have kind of stood the test of time, and they have helped us better understand our present day climate, but also kind of help predict our future. So an example, Sukuro Manabe was awarded the Nobel Prize in Physics in 2021 for his development of the first climate model at NOAA's Geophysical Fluid Dynamics Lab in Princeton back in the 1960s. And of course, many uncertainties exist with these models, with these full complexity models particularly. And that's the topic of my ongoing research, but also many, many others in the field. But it doesn't mean that they haven't been tremendously insightful and helpful. So before I kind of move on to the crux of the methodology and results, does anyone have any questions on these building blocks?
Can I ask a quick question?
Yeah, please.
Okay, in your satellite observed a trend in the Earth energy imbalance, right?
Mhm.
So then it seems like the plot is like he did a linear regression.
Yeah.
And I mean the data points are very low for this particular plot. So I'm assuming I mean what is your level of confidence? I'm pretty sure there's a lot of studies that's been done in that, and there's probably more data points used to create that. But I mean I'm just curious about like I mean where do you get the observations, and why use a linear regression to kind of fit the data or get some measurements?
Yeah, no, it's a good question. So the dots I show are like annual mean data points, which comes from very high resolution temporal points. So the satellites are observing twice a day. They cross the equator, which then gives us like across the planet many data points. And then they average it up to like a monthly mean value, like 30-day average. And then I further averaged it to an annual mean to show kind of like what's the overall change. But yeah, it's the actual amount of data that's behind this is an enormous amount of petabytes that's going that Earth is being observed by these NASA satellites. Regarding the linear fit, yeah, I mean, if you have a long enough time series and people do this for surface temperature, you can use like the final 10 years and the last 10 years, but right now we're only at 2 decades, and so it's better to kind of see what's the linear trend. I'm sure there's other statistical ways to get at like what's the overall d by dt of the variable. But all this other observational evidence has shown kind of similar values of the trends, and the uncertainty that I ascribed is pretty conservative is actually what it turns out to be also. And yeah, and that's a great question of like how does the actual observation, how much uncertainty and stuff is in it. I'm going to exactly talk about that now.
Thank you.
Yeah. All right, awesome. So I will leave also plenty of time at the end for questions, but so the methodology we use is fairly straightforward. We have observations of the Earth's energy imbalance, but again, observations tell you what is happening, but don't tell you why. And so on the left-hand side, we have this temporal anomaly. Delta is what I use that for, EEI, and then we get this from this series satellite observations. And on the right-hand side is kind of getting at the why. And ideally, we'd have many identical Earths and run experiments on all of them and then see what happens. But unfortunately, we don't have that. And so we only have one Earth. And so climate models are our best way to kind of currently simulate the planet's complexities in full detail. And they're governed by these physics, chemistry, biology laws that are tested against observations. And then we make sure they're simulating reality as best as one can. There's obviously limitations. So how do we use them here? The beauty of climate models is that you can identify each of these factors, the forcing, this effective radiative forcing, this external perturbation, the response to this, that's the lambda delta TS. So lambda is the climate feedback times the temperature response, gives you the kind of radiative response of the climate. And then internal climate variations all separately, this epsilon. So we can do experiments to kind of just isolate each of these terms. So first, we estimate internal variability's impact on the Earth's energy imbalance trend. We use models with no human influence and let the model just evolve on its own and see what's the range of trends you can get just from internal variability. Next, we kind of studied what would happen if you do put in forcing into the system and let the climate system respond to it. And so we do an important apples to apples experiment with the GFDL model, atmospheric model 4, where we prescribe the observed sea surface temperatures, so SSTs, and sea ice and the forcing, like basically try to get what the observations would do, but in the model. And so this is the model's best estimate of what Earth's energy imbalance is. And so that's the total of the right-hand side. And then to separate kind of the forcing from the response, we do an additional experiment where we held the forcing agents fixed. So we held greenhouse gases, aerosols, the sun, all of that fixed in the model. And then you only get the rate of response of the planet over the last 20 years because we still prescribe the observed 20 years of surface temperatures to the model. So the lower boundary conditions are being prescribed. So overall, we analyze the right-hand side, all to kind of figure out what's causing the observed trend. And I'll kind of go over each term separately, so there's no need to remember this. So first, I'll start off with the epsilon, the kind of the internal variability. What I plot here is the probability distribution of the trends in Earth's energy imbalance from 48 climate models of many realizations of the planet. So each realization is basically a 20-year trend in Earth's energy imbalance, that time series. And that's in the gray, that's the full range of trends you can get from internal variability, and it produces very naturally a nice Gaussian distribution. The black is the observations, and we assume a Gaussian distribution of observational uncertainty. As you can see, basically the take-home point is that observations lie well outside this kind of gray realm of noise. And for the few realizations that do stray into that observed range, we can quantify it and put a probability on it. And what we found was that there's a less than 1% chance that you could, in the same 2-decade period, get a high trend just from internal variability and a biased low trend from observational error. So we're pretty confident then that it's not just noise in the system that's producing this huge trend in Earth's energy imbalance. So what then produces this observed trend? In the atmospheric model, we only by including anthropogenic, that is human-caused, forcing changes and the associated response, so that's in the orange here, we get this kind of imbalance increase, where the orange line is now kind of this positive trend as well, just like the observations. When the forcing was fixed, so that's the response that's in the blue, the response alone actually produces a negative trend. So we're sending more energy to space. And I'll go into this a lot detail, but it's essentially because the observed SSTs, the sea surface temperatures, are increasing over this period. And so that actually increases the outgoing long-wave radiation to space. Importantly, we simulated 20 realizations each year over this period for both experiments to get at this kind of noise in the system as well. But you can see that all the realizations kind of show that increase in the orange. So on the right inset, I make it more clear. So instead of just the time series, I do the linear fit through each time series. You can see that the observations in the black cross with its pretty conservative error bars that we assumed, which now have been shown to be even smaller, lie outside those model control simulations in the gray. And in the orange, the model overlaps with the observations when human influence is included. And so the dots are the range of trends you get due to noise in the system. So what about the forcing is causing this positive trend in Earth's energy imbalance? What about this orange is giving us this big increase in the surplus of heat? And so we can, again, do further experiments to break down which agents in our planet are causing this. And so in 2001 to 2020, we found that there's about 0.5 watt per meter square per decade in forcing. And these further experiments show that about 80% of this is coming from greenhouse gas increases and the rest from aerosol decreases. And I'll explain that in a sec. But very importantly, the natural agents, such as the sun's brightness or volcanoes, that has a negligible contribution to the radiative forcing trend over this period, external perturbation. And so just 2 decades, that's about 1 watt per meter square of forcing we've put into the system. For reference, this 1 watt per meter square that we've put in the last 20 years, you compare it with the last 270 years, we've put in about 2.7 watts per meter square. And this is again from the IPCC's latest report. So we've basically put in about 1/3 of the forcing of the last 270 years in just the last 20 years. So very rapid changes to the system. And so in some ways, we should be kind of seeing this now in our observations. And if you recall the EEI equation, the ERF, the forcing plus the radiative response, we see that it's not the sun and the natural agent, so it must be then changes in the radiation emanating from within Earth. And so now we look at the outgoing long-wave radiation, which is basically in the infrared wavelengths. Sorry about the sign convention, but positive now actually means less heat in the system, and negative means more heat in the system, just because it means less outgoing radiation means more heat in the system. So black is again from the observations from the satellites, and then the best estimate from the model in the orange is we find a slight increase in OLR globally from the observations and from the model. And so we're actually seeing the infrared wavelengths is actually decreasing the imbalance. It's cooling the planet. And so this ends up being because the response in the blue alone actually causes a very positive trend. And then when you add in those greenhouse gases with the orange, it kind of flattens the trend. And what this ends up coming back to is kind of basics of Earth's outgoing long-wave radiation spectrum. Some kind of radiative transfer 101. This is a plot, global mean global mean outgoing long-wave radiation spectrum. And the black is from a different set of satellite observations, and in the blue is some model simulations we did. The y-axis is the outgoing radiation, and the x-axis is wave number. And so essentially the outgoing radiation follows a kind of a Planck function, and there's OLR, this curve itself can be connected then to certain gases as absorption and emission. And so in general, it follows this Planck function curve, but has bites out of the spectrum at CO2 wavelengths, at ozone, methane, and N2O wavelengths. Since their presence basically reduces the outgoing radiation to space. Given this powerful satellite mission, we can now see the time evolution at each channel, not just kind of the time average. And so here I show a channel from the CO2 wing and a channel from the methane and N2O band. And so the steeper, flatter trend on the left that you see is kind of from that CO2 channel. And so you can see a secular, steady, and consistent decline in emission to space that is less outgoing long-wave radiation from these gases. And for a while, we've had like a Keeling curve, what's been called in the climate science arena for CO2 concentrations, but not an accompanying heating curve. And so now we also, with this, we can now produce these long-term direct monitoring of the greenhouse gas impacts on the global heat budget too. So this is just for two parts of the spectrum. What about the rest of the spectrum? And so that top is the same from before, just the time average. And the bottom is now the trends, basically. How is that time average profile kind of changing with time? And so what you can see is that the observed spectral trends show a decrease in OLR in the CO2, methane, and N2O bands. And then in the water vapor band and the window band, so window is basically kind of this less opaque part of the Earth's atmosphere where energy can escape, there's been more energy escaping from it now. And so kind of, you can already see spectrally the reason for the outgoing long-wave radiation increase, kind of the broadband. Why is long-wave cooling the planet? It simply comes down to there's more infrared radiation escaping to space from the window and water vapor bands, which then exceeds the well-mixed greenhouse gases bands decrease. Our model simulations were able to reproduce these observed trends, the green and blue on the right with the black, whether we give it this time period's conditions in blue, or whether we kind of did these very idealized climate change conditions and then scaled it to this period in the green. And so we were able to kind of identify climate change directly in these infrared spectral observations. Mm-hmm. So we break down this blue curve on the left kind of further. So we decompose it into the forcing and feedback. And here we say the OLR, the outgoing long radiation. The nu is just at each wave number we do this. And we're doing this kind of globally at each grid box at each time, at each month. And then we just do a linear trend through it to get our trends out. And so what we see in the red, basically, so the equation at the top is showing that the OLR can be broken into the sum of the change in the instantaneous rate of forcing in red, and then the adjustments plus the rate of response of the planet in the brown, I guess. So the instantaneous rate of forcing, essentially, this is the immediate effect of well-mixed greenhouse gases increasing in the planet is to just decrease the OLR. It's blocking that outgoing radiation from going to space. You'll see one exception at where there's actually an increase in that red curve due to in the center of the CO2 band, and this is mostly due to the emission level going up when you add CO2, and in the stratosphere that's actually at a warmer temperature. The adjustments is basically dominated by stratospheric cooling. So from the 60s, we have known that when you add CO2 to the atmosphere, the stratosphere cools. And in the center of the CO2 band, where this is where it kind of emits radiation, you can see that this stratospheric cooling has decreased the outgoing radiation to space. So less, it's a cooler planet, it also emits less radiation to space. And this also happens in the ozone band. Ozone is also abundant in the stratosphere. And finally, the response of the planet to these imposed perturbations from these gases and whatnot is that a warmer planet, a warmer Earth, leads to a larger Planck response. So you just shed more heat to space. So that's that brown curve is kind of uniformly positive throughout the spectrum. And so essentially it's saying that the atmospheric window, there's more surface emission that's getting out to space, but also there's more atmospheric emission out to space too. And to kind of put it all together, these all kind of together produce an increase in OLR that's cooling the planet, that's decreasing Earth's energy imbalance. And so kind of three bedrock principles of climate change physics we were able to identify in this very fine resolution spectral satellite record of the infrared is this increasing greenhouse effect, stratospheric cooling in the center of the CO2 band we can see, and also surface tropospheric warming. So it's nice that we were able to boil it down to some key principles in the infrared. But the whole premise I started with was that Earth's energy balance is increasing, it's not decreasing. So if it's not the long wave, this infrared causing the imbalance, what is? So finally, we look at the reflection of sunlight, that other piece of outgoing radiation. And what we find is that, again, the sign is that negative means heating here. So less reflected sunlight means more heat in the system. And what we find is that there's been a massive decrease in reflection globally. So that's that black curve in the observations. The feedbacks and the response in the blue kind of alone gives you a slight decrease in reflection in the model, but when the forcing in that orange is then included, this trend line kind of tilts much more downward. So why is this happening? What about this forcing is causing this? And a lot of it is to do with this forcing. So we can again break down now in just the reflected solar, what are these external perturbations causing to the energy balance of the planet? So all the agents together causes about a negative 0.28 watts per meter square per decade trend. So this means less sunlight is being reflected solely by these greenhouse gases and aerosols that's together causing this much of a change. Now we can further see that greenhouse gases is about 40% of that, and then the aerosols about 60% of that or so. I won't go into the greenhouse gas one too much, but essentially greenhouse gas is increasing in the Earth's atmosphere, decreases the cloud top rate of cooling directly, and this decreases the cloud cover, which then decreases reflection. So if you're under a white bright cloud, you have nice shade, but when that white bright cloud goes away, you're now, the sun's shining on you more, so that's more absorbed solar radiation. But the aerosols is what I'll kind of explain more right now. Kind of a primer on what is aerosol radiation cloud interactions. There's two essential main effects. There's the direct effect, where if you think of New York or London in the 20th century, or India or China in the 21st century, rapidly changing economies, developing, industrializing economies, there's just a lot of these aerosols in the atmosphere. And so when you have more of these aerosols in the atmosphere, you kind of don't reflect back, reflect back more and more sunlight. It doesn't reach the surface as much. Now there's also the indirect effect, where aerosols can actually change the makeup of a cloud. And one indirect effect is, which is the second indirect effect, on the left-hand right-hand side, the left part of it, think of a pristine cloud where you have efficient precipitation, the liquid water cloud of the cloud is being depleted, and so then the cloud cover kind of dissipates. Now, in a more polluted environment on the right side, you have these much smaller droplets, which take longer to get to raindrop coalescence size. Sorry, they take longer to coalesce to raindrop size. And so it's less efficient to precipitate out, and so that leaves more liquid water in the cloud. And so this also leads to more cloud cover, and this mainly means more reflection and higher albedo by the clouds. Now, what's happened now in the last 20 years has been kind of the flip, where we're going from a dirty environment to a more pristine environment. So there's been clean air laws in the United States, Europe, China that have been decreasing these aerosols, these light reflecting particles, so that direct effect, but also we found that the cloud liquid water path has been decreasing, going back to this pristine environment. And so in the right-hand side, I'm showing not the global mean, but just the northern extratropics. Just to remind you, the black observations are basically in that cross with its error bars. And then the gray is the control simulation. So the decline in reflection from the northern extratropics, so 30 to 60 north, is happening. And it's not just a random thing. The noise kind of can't explain that. But when you have the radiative feedbacks in the blue, it kind of gets you that decrease in reflection, but it's only when you put this forcing changes in, the actual atmospheric aerosol concentrations allowed to change in the model, do we then agree very well with the observations in the black cross. And so both this direct and indirect effect is what we're kind of attributing the decrease in reflected solar radiation from the 30 to 60 north average area. And so we find this massive decrease in reflection across the globe. I'm just showing you now all the parts on the right-hand side, the tropics, northern extratropics, southern extratropics, poles. And so forcing helps explain about 40% of this reduction in reflection, so from those greenhouse gases and aerosols. But also in response to the forcing, I want to point out that temperatures rise and the sea ice melts at the poles. So on the far right, you can see actually that there's been a decrease in reflection, and this is area average, so it's still a substantial contribution to the global change. And so sea ice reduction, again, reduces reflection because ice is bright and white, so it reflects sunlight, and when it decreases, that reflection also decreases because open ocean water is a darker surface. We also found with separate calculations that water vapor also increased over this period, and this water vapor mostly thought, to absorb in the infrared, which is correct, but it also has a near IR absorption, which is in the short wave. And that also then reduces the top of atmosphere reflection. And all that is in the blue dots, basically. Now you may ask, what about the clouds' role in this feedback? I showed you, that's kind of been an uncertain aspect of our climate system, how it responds to climate change, and how do they contribute to this reflected solar radiation decrease and OLR increase? So yeah, if you go back to the climate feedback kind of linearization, it can be broken down into that Planck feedback, water vapor feedback, surface albedo feedback, and cloud feedback. And I've spoken about those first three terms a fair amount. But what about this cloud feedback specifically, which is the radiative response of the clouds to surface warming? And so here on the left figure, I basically show in the black cross, the cloud radiative effect trends. Basically the impact of clouds on the Earth's energy imbalance, but how now that's changing with time as a trend. And I kind of removed some artifacts from it, which don't allow you to kind of say it's exactly the cloud feedback, namely the cloud masking and the cloud and some forcing associated with it, the red and the light blue. But essentially what we find to get this best estimate of the cloud feedback from observations is that the long wave cloud feedback is negative and essentially adding to that OLR increase. And in the short wave, the cloud feedback is positive. So this means that it's that reduction in clouds that is then causing more sunlight, less sunlight reflected. which is a positive shortwave cloud feedback.
Mhm.
Now, the interesting part is that the net cloud feedback ends up being pretty weakly positive, but again, now with large uncertainty. So we still can't figure out from the current observations whether they are amplifying or diminishing global warming. But why is this negative long wave cloud feedback happening and this short wave cloud feedback positive case happening? And why is the net cloud feedback kind of then canceling between the two? Is it fortuitous, or is that some more physical principles we can attribute this to? And so it has to do a lot with tropical high clouds. Tropical high clouds, if you think of like on a summer afternoon, usually you'll see this big thunderstorm cloud and then these anvil clouds around it. So those are examples of high clouds. There's also cirrus clouds, etc. They're very important radiatively for the Earth's energy budget. And what we found from just a strictly observational analysis is that this total high cloud feedback is only slightly positive, again, because of this strong long wave, short wave cancellations. The red is long wave, blue is short wave here. And you can break it down into how much of this is coming from changes in its amount, so its coverage, which has been called the iris feedback, changes in its vertical axis, so the altitude, which has kind of been attributed to a fixed anvil temperature paradigm, and also then the optical depth of the cloud, so how much thicker or thinner is a cloud optically with light. And so what we find is that the tropical high amount feedback is near zero due to these strong cancellations between the long wave and short wave components, where we found a decrease for the kind of peak high cloud cover in the tropics. And so that's very radiatively relevant. So when you contract those clouds, you can let more outgoing long wave radiation to space, but it also decreases the amount of short wave reflection. So that's that negative positive that's happening. The tropical high cloud altitude feedback is positive because these high clouds are rising. Essentially, these high clouds act like as a greenhouse effect. And so when they when they kind of stay at the same temperature, but the surface warms, that greenhouse effect increases even more. And finally, the tropical high cloud optical depth feedback, so is near zero, again, because we find that of this long wave, short wave cancellation. And we found that the ice in those clouds is decreasing, which then allows more outgoing long wave radiation to space and then also reduces the albedo. So it's reflecting less sunlight, which is a positive short wave feedback for the system. So kind of my conclusion and broader conclusions on how Earth is accumulating heat. Earth's energy imbalance, EEI, is increasing at the rate of almost 0.4 watt per meter square per decade. We found that it was exceptionally unlikely that the observed trend in Earth's energy imbalance can be explained by internal variability alone. Instead, anthropogenic forcing and feedbacks kind of yields the observed TEI. Now, although it's a 2-decade period only, we found that it's exceptionally unlikely, showing the kind of magnitude of the changes were put in the system. So the observed increase in Earth's energy imbalance, then we found doesn't come from the long wave changes, but instead from this decreased shortwave reflection. And so we always think, increasing greenhouse gases means trapping more infrared heat. This classical greenhouse effect becomes larger. And so that's correct, as you saw in that spectral plots. But the flip side is that the resulting warmer planet also radiates more infrared heat to space. And so the greenhouse gas heating impact is canceled. Instead, much of this imbalance then kind of increasing comes from the fact that we're receiving the same amount of sunlight, but we're reflecting back less and less. And this is because of those increased greenhouse gases, less aerosols in the air to reflect the light, sea ice decreases, kind of all together are additive, where the forcing and feedbacks are adding together to decrease reflected shortwave radiation. And so put very simply, in response to external forcing in both long wave and shortwave radiation, Earth has a stabilizing feedback only in the long wave, that Planck feedback, and not in the shortwave. So the planet continues to accumulate heat in the shortwave spectrum. And so here are the references for the work I've spoken about. And of course, I'm
Mhm.
more than happy to take any questions now or later offline too. Thank you.
Wow.
Okay, great. Thank you very much for that really interesting talk. This is the kind of stuff that I think is really great to hear. So yeah, let's thank our speaker and appreciate it. And then of course, we have some time for questions. If anybody has any, please go ahead.
I have a question. So, first of all, a very clear talk. Thank you so much. It really interesting to see how deep you have to dig into these numbers to get some information out of them. The argument that incoming and outgoing radiation balance each other. That's essentially you're talking about the difference of large quantities. And climate deniers, people who are critical of climate science, always use it as an argument to sort of poo-poo the results, right? I think your talk gives more or less substantive evidence that yes, it is a difference between large quantities, but still we can control the difference. Is that correct? A correct statement? I mean,
Yeah,
that
I
would be
think
the argument that we could use against these deniers who say, well, it's difference of large numbers. There's lots of uncertainty.
Yeah, I mean, empirically, it is very hard to detect the difference between the large numbers from satellites. But that's why actually the satellites anchor themselves to what's called Argo ocean observations. So we have these like little buoys all across the world's oceans that are measuring the heat content of all the way to 2,000 meters in the ocean. And those observations independently from the satellite also show the increase in Earth's energy imbalance. But even
Right, yeah.
getting that
Yeah.
absolute value is coming mostly actually from the ocean observations, not from the satellite. But the rate of that's being shown is just consistent across many, many independent ways of observing the planet.
Right, right. Good.
Yeah.
Very good work.
Thanks.
Thank you.
Any other questions?
One quick question. Very nice talk. Thank you, Priyam, for this very informative talk. So you talk about greenhouses increasing, right? And stratospheric cooling, but there is also the effect of ozone depletion.
Mhm.
And then, so does your model include like ultraviolet radiation coming from the sun?
Yeah. So it's ultraviolet would be in the shortwave radiation that's in there. The direct impact of ozone we found was not too high, especially over this period of 2001 to 2020. The ozone hole is kind of like repairing itself, so the temporal change itself is not so much, so it wouldn't show up as a big signal in our global mean results. But yeah, it is in there. The ozone changes are in the atmospheric model. Yep.
Thank you.
Okay. Any other questions?
Go ahead.
Sorry, go ahead.
No, I'm hoping also to kind of reconnect with MCRN and, when you look at observations, you're kind of forced to use full complexity models. But I'm hoping to kind of go down the hierarchy and start relooking at simpler models as well. So any ideas or cross collaboration, I'm really excited about too.
That actually leads into my question. So I mean, I'm kind of curious. So I work at the Joint Center for Satellite Data Simulation. So I'm writing DA code for complex models. But with a math background, I'm also interested in reduced order models. And so I was going to ask if there's any kind of interest in, some, I don't know, code set or something where it would be easy to prototype reduced order models connected to a DA system to assimilate these kinds of observations, to do things like parameter estimation, sensitivity studies, things like this. If that's sort of if you think there's a need for something like that, because as it stands, everybody sort of has to write their own thing. And even some of these simple models might be well suited to an HPC environment anyway when the data gets large enough, right? Or the number of the degrees of freedom get large enough. Yeah, I just wonder if there's any sort of interest in that, or what you think about those kinds of things. Yeah.
Yeah, I mean, I'm not too much of an expert on data assimilation DA, but I do think, reducing complexity and trying to, remove one thing at a time and see what's still working in the model, and is it still giving you the main features of the climate, the main changes in the climate, I think are pretty critical. In our field, there's been a lot of like huge advances that we made by using aquaplanet simulations. So this is a planet without any land. So you don't have to worry about the continental configuration or anything. And a lot of like theories about, what we had about monsoons, about Arctic amplification, all that was kind of changed just by realizing that just ocean atmosphere interactions are needed, not land as well. That's just one example of how you go down this model hierarchy. You can kind of learn more and more about the very complex system, but we can try to boil it down to these kind of basic principles. And I think there's been a lot of work on the long wave side of things, where in the infrared, there's been some more analytical efforts to constrain these forcing and feedbacks. You still need a model at the end of the day, but there's some paper and pencil estimates out there, and there have been in the actual models that we use in climate models, how the atmosphere cools to space has been like simplified tremendously from the 50s and 70s, and that's still being used today. And if we weren't using that, my point is it would be a very computationally expensive problem. So kind of bridging those two, if you can make simpler approximations, it actually ends up helping the climate modeling effort itself computationally.
Yeah, interesting. Yeah, that's one thing. One way I think data assimilation is useful for climate studies. I mean, it's often a numerical weather prediction thing, 2 weeks out sort of thing, but is really parameter estimation for whatever parameterized scheme you're looking at or trying to use in conjunction with the development of a reduced order model. It's always sort of interesting to me. Yeah. Okay, cool. Yeah, that's really cool and really interesting talk. Any other questions oh, sorry, I did want to mention, popped into my head. I don't know if so Ian Eisenman did some really interesting work looking at complexity with different sea ice models and forcings and feedbacks. Just, I don't know if you had seen that. It was sort of interesting, the interplay between, these larger scale numerical models and then even down to a simple ODE for ice itself, just an energy balance model. If you've read it, I don't know, but if not, I could send you the paper. It's
I know of his work, but I haven't seen that exact paper yet. Yeah, so I'll check it out.
Okay, sure. I'll send it to you.
Cool.
It's just interesting. Yeah. Yeah, sorry. So any other questions? Okay, perfect. Ending basically exactly on time. And so let's thank our speaker again. And
yeah, thanks for having me. I really appreciate it. Yeah.
Oh yeah, absolutely. Yep. Okay, great. Then I guess we will see you all next week.
Thanks.
Yes, cheers.
Okay, bye.